Removal of methyl orange, MO, by Chitosan modi.ed by 0 valent iron. Abstract. This work focuses on MO sorption by Chitosan, nZVI/Chitosan and nZVI was investigated. The purpose of this study is to understand the mechanisms that govern the elimination of MO and to find a suitable kinetics model of removal. Spectroscopic studies including FTIR, TG-DSC, methylene blue, and iodine number and effect of pH were used for its characterization. Equilibrium data was examined using a comparison of linear Langmuir, Freundlich, and Temkin isotherm models. The Freundlich isotherm provided the best fit to the experimental data for MO as indicated by the values of the regression coefficient. The kinetic rates were modeled by using the Lagergren-first-order, pseudo-second-order, Elovich and Intraparticle diffusion model. The pseudo-second-order model was found to explain the adsorption kinetics most effectively. The presence of intra-particle diffusion mechanism was prominent, although it was not the sole rate-determining step. The results showed that Chitosan, nZVI/Chitosan and nZVI, can be effective for removing MO from solution. Keywords: adsorption, Chitosan, nanoparticle, 0 valent iron, methyl orange. 1. Introduction. Water touches all aspects of development and it is the center of almost all of the goals of sustainable development. It stimulates economic growth, promotes healthy ecosystems and is essential for life. Faced with strong demographic growth, humanity has resorted to industrialization and modernization to meet its needs. Paradoxically, this industrialization causes damage to the environment. Particularly the massive production of solid waste, water pollution due to the dumping of a wide variety of chemicals, synthetic dyes, heavy metals and many others, in the water cycle thus endangering this resource. Indeed, in printing houses, food industries, cosmetics, and pharmaceuticals, but especially in the textile industry, Taylor Poshti and AL, 2001, dyes are widely used for their chemical stability, ease of their synthesis and color variety. These dyes, in this case methyl orange, are at the origin of pollution once discharged into the environment. Studies have shown that several azo dyes are toxic and mutagenic, Kede and AL, 2011. The heterogeneity of their composition makes it difficult if not almost impossible to obtain pollution thresholds lower or equal to those imposed by environmental standards, after treatment with traditional techniques. Several conventional techniques have been developed to remove dyes from water. The best known and most used are the biological and physicochemical methods, coagulation/flocculation, reverse osmosis, chemical oxidation, ion exchange, electrochemical methods. In addition, energy demand is high, range Abishiyam and AL, 2013. For several decades, adsorption has not ceased to seduce the scientific community because in general, it is a simple separation process, inexpensive, free of byproducts and above all effective. The speed, reversibility, and simplicity of the apparatus constitute the main advantages of adsorption as a technique for removing organic and inorganic pollutants in water. Adsorbents commonly used are activated carbon, polymeric materials, clays, biosolvents, Rajkumar and AL, 2014. Research work has been conducted to develop adsorbent materials at low cost using natural waste from agriculture and animals. The use of this waste for the synthesis of adsorbent materials contributes to the protection of the environment, the reduction of waste disposal costs and the valorization of these. We were interested in the synthesis of an available and inexpensive adsorbent, Chitosan prepared from the crab shells for the elimination of methyl orange. These shells come from the recycling of discharges from the fishing industry, animal waste available throughout Cameroon. Some adsorbents are characterized by a low adsorption capacity, higher cost, a longer equilibrium time, and low regeneration capacities. To improve their performances, one can proceed by incorporating additional chemical substances capable of giving them magnetic properties. This method has been widely used in recent years due to its simplicity and high speed. Hababa and collaborators obtained a maximum adsorption capacity of 416.1 mgg1 for the absorption of methyl orange on a nanocomposite of Chitosan glyoxal, Hababa and AL, 2018. Mohammed et.al. Synthesized a composite nanofibrous Chitosan alcohol polyvinyl zeolite membrane for the adsorption of methyl orange. The adsorption capacity of the membrane was 153 mgg1, Mohammed et.al., 2019. In 2010 Zhang et.al. showed that more than 98% of Pb2+ ions in wastewater had been eliminated using kaolinite impregnated with 0 iron nanoparticles. A similar approach gives us the enthusiasm to study carefully the elimination of a dye, methyl orange by a biosolvent impregnated with 0 iron. So far, the removal of MO using CHT, CHT/nZVI, nZVI, adsorbent has not been a lot reported in the literature. Hence, the main objective of this investigation was to examine adsorption characteristic for MO on modi.ed CHT by iron nanoparticles, CHT/nZVI, coded on it. The effects of such factors as contact time, pH, as well as isotherm and adsorption kinetics were also studied. 2 Materials and methods 2.1. Sampling area and adsorbent. 2.2 Preparation of CHT. 2.3 Preparation of nZVI and CHT/nZVI. 2.4 Adsorbate preparation. 2.5 Solid phase characterization of CHT, CHT/nZVI and nZVI. 2.6 Aqueous adsorption characteristics 2.6.1. Iodine number. 2.6.2 Methylene blue adsorption test. 2.7 Batch adsorption studies. The crab shells used as raw material in this study comes from the mangrove of Nzugue, Douala, Cameroon, 4 degrees 8 minutes north and 9 degrees 49 minutes east. Then the sample was grinned in a mortar and sieved to pass through 125 m mesh size. The biomaterial sample was stored in sterile, closed plastic containers and used as an adsorbent. Production of this Chitosan is based on chitin derived from shells of crabs. The steps in the extraction of chitin from shells are the removal of proteins and minerals, such as calcium carbonate and calcium phosphate, by treatment with alkali and acid respectively. Before chemical treatment, the shells are ground to improve the efficiency of treatment, and after final rinsing the chitin are dried and can be stored as a stable intermediate. The deacetylation of chitin through treatment with strong NaOH is carried out at elevated temperature over a controlled period of time. To achieve the highest possible yield, the material is kept in the solid state. To prepare a filterable grade product, an additional step is added, including solubilization in an appropriate organic acid. The acid solution is then filtered through specified mesh size filter before spray drying. In contrast to the regular grade Chitosan, this latter form is water soluble. Water soluble industrial grade Chitosan is made by regular dry blending of Chitosan with an appropriate acid. These Chitosan production processes are summarized in Fig.1. Green tea extract was prepared by heating 20 g/L green tea to 80 degrees C followed by vacuum filtration. A solution of 0.1 mFe2SO 4.7 H2O was prepared by dissolving 16.2 grams of solid Fe2SO 4.7 H2O in 1 L of deionized water. Green tea synthesized nanoscale 0 valent iron, nZVI, was then prepared by adding 0.1 MFE2 so 4.7H2O to 20G/L green tea in a 2:1 volume ratio, Hogan al. 2009. To obtain CHT/nZVI, 10 grams of Chitosan was added to a solution of 0.1 MFE2 so 4.7H2O then stirred for 45 minutes. To obtain mixture a solution of 20G/L of green tea was added. The CHT/nZVI were separated and immediately washed many times with water and dried. All the chemicals used in the present work were of analytical reagent grade obtained from Aldrich Chemical CO. A methyl orange stock solution of 1000 mgl1 was prepared by mixing 1 gram of methyl orange in 1 L of deionized water. This stock solution was serially diluted to get the appropriate concentrations for conducting adsorption experiments. The pH at the potential of zero charge of the CHT/nZVI and nZVI was measured using the pH drift method. The pH of the solution was adjusted by using 0.01 m sodium hydroxide or hydrochloric acid. Nitrogen was bubbled through the solution at 250 degrees C to remove the dissolved carbon dioxide. 100 mg was added to 50 ml of the solution. After stabilization, the final pH was recorded. The graphs of final pH versus initial pH used to determine the 0 point charge of the CHT/nZVI and nZVI, Lopez and al., 1999. The CHT/nZVI and nZVI, activation temperature was fixed using thermogravimetry and differential thermal analysis, TG-DSC. A Fourier transform infrared spectroscope, FTIR, Nicolay 6700, Nicolay, USA, was used to evaluate the distribution of functional groups on the surface between different materials at a resolution of 2 cm1. The iodine number was determined by using the sodium thiosulfate volumetric method. Standard iodine solution was added over adsorbents, 100 mg, and after an equilibration time of 5 minutes, the residual iodine concentration was determined by titration with standard sodium thiosulfate using starch as an indicator. The iodine number was defined as the adsorbed quantities of iodine, mol.G1 of adsorbents, obtained by subtracting the residual concentration at equilibrium Ce, from the initial concentration C0, where M and V are the mass of adsorbent sample and the volume of adsorbing solution respectively. The samples of CHT/nZVI and nZVI were investigated for their aqueous adsorption of dyes using methylene blue. Adsorbent samples, 100 mg, were mixed with methylene blue in 50 ml stoppered Erlenmeyer flasks. Batch experiments were carried out in the shaker at room temperature for 2H. The solutions were filtered and the concentrations of solutions were then determined by spectrophotometer at 659 nm. Then the quantity adsorbed was also calculated, mol.G1, for CHT/nZVI and nZVI using equation 1. The adsorbate stock solution of 1000 mgl1 of methyl orange was diluted as required to obtain standard solutions containing 10 to 60 mgl1. Batch mode adsorption studies were carried out with 50 mg of adsorbent and 50 ml of methyl orange solution of a desired concentration in 200 ml conical flasks and were agitated for predetermined time intervals at room temperature in a mechanical shaker. The removal kinetics of methyl orange were investigated by taking samples of the solution after the desired contact time, 0120 min. The residual concentration of methylene blue was determined using SpectroQuant Faro 300 spectrophotometer at 465 nm. 3 results and discussions. 3.1. Characterization of CHT/nZVI and nZVI. This spectra range from 4000 to 500 cm1. The broad bands at 3292 cm1, 3254 cm1 and 3209 cm1 for CHT/nZVI and nZVI respectively are attributed to intermolecular hydrogen bonds and to the elongation vibration overlap between the OH and NH bonds. In addition, the 2876 cm1 band for CHT corresponds to the elongation vibrations of the aliphatic CH bonds, due in AL, 2014. The peaks at 1654 cm1, 1620 cm1, and 1614 cm1 respectively for CHT/nZVI and nZVI correspond to the elongation vibration of the C=O bond of the carbonyl group. The peaks at 1419 cm1 and 1375 cm1 for CHT, 1425 cm1, 1375 cm1 for CHT/nZVI and 1423 and 1338 cm1 for nZVI correspond to the CN bond, Malkoch and AL, 2014. The peaks at 1149 cm1 for CHT, 1151 cm1 for CHT/nZVI and 1202 cm1 for nZVI are those of the COC bond. The vibration of the CO bond of alcohols is characterized by bands at 1058 cm1 for CHT, 1072 cm1 for CHT/nZVI and 1075 cm1 for nZVI, ready in AL, 2007. The bands 1026 cm1 for CHT, 1008 cm1 for CHT/nZVI and 1017 cm1 for nZVI are characteristic of the OC bond. However, out-of-plane vibration of the CH link is characterized by peaks at 892 cm1 for CHT, 952 cm1 for CHT/nZVI. On the other hand, peaks at 514 and 440 CHT/nZVI, 592 and 512 for nZVI are characteristic of the FeO bond, Yang et al., 2014. We note that the characteristic peaks of the CH and COC bonds of the CHT have almost disappeared in the CHT/nZVI. The characteristic peaks of the C=O, NH and CN bonds of the CHT are more intense in the CHT/nZVI. The characteristic peaks of the FeO bond are present on the CHT/nZVI, nZVI and absent on the CHT. The impregnation with nZVI has therefore changed the structure of the CHT/nZVI by opening the heterocycles, removing the methyl groups and incorporating the iron into the matrix of the latter. The result of thermogravimetric analysis of CHT/nZVI and nZVI coupled with differential scanning calorimetry are shown in the Fig 3, 4, and 5. From Fig. 3 which represents the thermogram of CHT, we note that the thermal degradation profile occurs in 2 stages. The first indicates the loss of water in the sample and appears in the area between 50 degrees Celsius to 110 degrees Celsius and correspond to a loss of mass of 12.80%. The second loss of mass, with a high speed of loss of mass, is recorded in the temperature range between 250 degrees Celsius, 410 degrees Celsius corresponding to a mass loss of 76.55% can be attributed to the degradation of the polymer chain of Chitosan. Mass loss continues gradually and slowly up to 600 degrees Celsius. The thermal decomposition of CHT/nZVI, Figure 4, occurs in 3 steps. The first and the second steps correspond to the evaporation of water and the degradation of the polymer chain of Chitosan respectively, while the third step corresponds to a wave loss of 21.16% in the temperature range of 350 degrees Celsius to 650 degrees Celsius. This loss of mass is attributed to the degradation of the organic matter resulting from the impregnation of the Chitosan by the nanoparticles of iron 0. Iodine and methylene blue adsorption are considered a simple and quick test for evaluating the porous structure of micro and mesoporous adsorbents. Iodine has a small molecular size and can readily penetrate deep micropores of the CHT/nZVI and nZVI. So iodine number gives approximate measure of the micropore content of the CHT/nZVI and nZVI. Likewise, methylene blue number indicates the mesopore distribution in the adsorbents and indicates the ability of CHT/nZVI and nZVI to adsorb medium-sized molecules. In an MBN of CHT/nZVI and nZVI is shown in Fig. 5 and Table 1. CHT/nZVI and nZVI are essentially micropores with a more pronounced microporosity for nZVI. The value of pH-ZPC is 7.8 for CHT, it is therefore of a basic nature and on its surface, basic groups are predominant. However, the pH-ZPC values of CHT/nZVI and nZVI are 5 and 4 respectively, they are acidic in nature and acidic groups are predominant on their surfaces. These values tell us the suitable range for the adsorption of methyl orange. When the pH is lower than the pH-ZPC, the surface of CHT/nZVI is protonate, it is positively charged. At pH S above pH-ZPC the hydroxyl ions neutralize the positive sites and the surface then charges negatively. In addition, at pH below the pKa of methyl orange, 3.9, it occurs in the cationic form, acid, and develops a repulsion opposite the adsorbent. 3.2 Effect of contact time. The time necessary to reach the equilibrium of adsorption of MO onto CHT/nZVI and nZVI was investigated at initial concentration of 50 mg/L. Experiments were performed using a solid-liquid ratio of 1g/L and lack of the other number. The variation of adsorption capacity as function of contact time for MO on CHT/nZVI and nZVI, are shown in Fig. 8. Results indicate that the rate of adsorption of MO are fast for the first 5 minutes and thereafter slowed gradually until the adsorption reaches equilibrium at about 45 minutes. A large number of vacant active sites are occupied by the MO during the initial time of contact. After a period of time, the vacant surface sites are difficult to be available because of the repulsive forces between the MO adsorbed on CHT/nZVI and nZVI surface and the MO in solution. Therefore, the mesopores on the surface of CHT/nZVI and nZVI were saturated with MO in the initial stage of adsorption. Thereafter, the MO have to traverse farther and deeper into the pores encountering much larger resistance. Alpha et al. 2016. 3.3 Effect of pH. Fig. 8 shows the effect of the initial pH on the adsorption of methyl orange by CHT/nZVI and nZVI for a dye concentration of 20 mg/L. The adsorption capacity is maximum in an acid medium, more precisely when the pH value is lower than the pH-ZPC of each of the adsorbents. A general observation of the figure shows that the amount of orange methyl adsorbed decreases when the pH value is higher than pH-ZPC. This phenomenon is justified by the acid-base behavior of methyl orange. Indeed, the orange methyl is an anionic dye, carries the negative charge. In acid medium the H and ions are predominant in the solution, therefore, the vacant sites of the adsorbent will be occupied by these cations, and the orange methyl molecules will be adsorbed by the positive sites of the support. In other words, as the pH of the system increases, the number of negatively charged sites increases unlike that of the positively charged sites which decreases. The negative charge of the adsorbent sites therefore does not promote the adsorption of the dianions due to electrostatic repulsion. In addition, the low adsorption rate of methyl orange at alkaline pH is due to the presence of excess O ions, which will compete with the anionic molecules of dye for the adsorption sites. 3.4 Kinetic Studies. The adsorption kinetic study is important for determining the efficiency of adsorption and for determination of the adsorption rate, limiting steps being necessary in order to define the rate parameters for design purposes. Kinetic data obtained from the adsorption study of MO were predicted with different models widely applied to describe the adsorption behavior of MO on CHT/nZVI and nZVI. In order to determine the mechanism of adsorption and its potential rate controlling step, the tested models were the pseudo-first-order model, Nzugue et al. 2015, pseudo-second-order model and intra-particle diffusion model, Valent et al. 2013. Intra-particle diffusion model. The pseudo-first-order and pseudo-second-order kinetic models were applied to predict the mechanism involved in the adsorption process of MO. The linear form of the pseudo and second-order model were given by 2 and 3. It is clear from obtained data of Table 2 that pseudo-second-order kinetic model is more able to provide a successful description of MO adsorption onto CHT/nZVI and nZVI. The kinetic parameters and the correlation coefficients values determined from the slope and the intercept of these plots are illustrated in Table 2. The calculated adsorptive capacities values from the pseudo-second-order model are in a good agreement with those experimentally determined. Moreover, the correlation coefficient values are quite well 0,982, and much higher than those found by the pseudo-first-order kinetic model. Thus, we can assert that the adsorbent systems are well described by the pseudo-second-order kinetic model. Intra-particle diffusion model is given by 4. It can be seen from curves regarding the effect of contact time, 3 distinct steps, the external diffusion, the intra-particle diffusion and equilibrium stage. The first slopes covering the time range between 0 to 5 minutes, must be the external diffusion. This is related to the binding of MO by active sites which are distributed onto the outer surface of the adsorbents. The second linear portions included the adsorption period of 5 to 45 minutes, is assigned to the gradual adsorption limited by diffusion of MO in the micropores of the adsorbent particles, the intra-particle diffusion. The third linear portions included the time period of 45 to 120 minutes, which denotes establishment of the equilibrium. The values of the correlation and the diffusion rate constants were determined from the Weber and Morris model and reported in Table 2. High correlation coefficient values suggest an important relationship between Qt and T1/2 resulting from the adsorption of MO onto CHT/nZVI and nZVI. 3.5 Equilibrium isotherms. The isotherm adsorption studies were investigated to determine the maximum adsorption uptake for MO on CHT/nZVI and nZVI. Isotherms were evaluated using the commonly used equilibrium model, Langmuir, Freundlich and Temkin models, Tchakounte et al. 2019. Langmuir linear equation. Where QE is the equilibrium MO concentration on the adsorbent, mgg1, CE is the equilibrium MO concentration in the solution, mgl1, Qmax adsorbent, mgg1, and Kl is the monolayer adsorption capacity of the Langmuir adsorption constant, Lmg1, related with the free energy of adsorption. Fig 9 and Table 3 indicate the linear relationship between the amount, mg, of MO sorbed per unit mass, g, of CHT/nZVI and nZVI against the concentration of MO remaining in solution, mg/L. The coefficients of correlation, R2, grouped in Table 3 indicate that the adsorption of the MO onto CHT/nZVI and nZVI don't .t well the Langmuir model. In other hands, the sorption of MO onto CHT/nZVI and nZVI was taken place at the functional group/binding sites on the surface of the CHT/nZVI and nZVI, which is regarded as monolayer bisorption. The Freundlich model assumes active sites of difference energies in a heterogeneous adsorption surface. The Freundlich model, Kede 2015, is where Kf is a constant relating the adsorption capacity and 1/n is an empirical parameter relating the adsorption intensity, which varies with the heterogeneity of the material, Fig. 10 in Table 3. The higher R2 of the Freundlich model implied a greater tendency of the heterogeneous surface of CHT/nZVI and nZVI for the removal of MO. The low value of 1/n in the Freundlich isotherm suggested that any large change in the equilibrium concentration of MO would not result in a sinus change in the amount of MO adsorbed by CHT/nZVI and nZVI. The Freundlich constant n is found to be greater than 1, which indicates a favorable condition for adsorption, Rongbing and al. 2015. The Temkin isotherm contains a factor that explicitly takes into account of the adsorbent-adsorbate interactions. In this equation, it is assumed that, because of these interactions and ignoring very low and very large concentration values, the heat of adsorption of all molecules in the layer would decrease linearly with the coverage, Lagergren at Luanga and al. 2010. The linear form of the Temkin model is written as QE equals BLNAT plus BLNC, 7. Where it is the equilibrium binding constant corresponding to the maximum binding energy, B equals RT/BT, B, J/mol, is the Temkin constant related to the heat of adsorption, R, 8.314 J/mol K, is the universal gas constant and T, K, is solution temperature. The values obtained from the Temkin isotherm, Fig. 11 in Table 3, indicate that the adsorption of MO onto CHT/nZVI and nZVI occurred via chemisorption. The values for it were higher than 8 kJ/mol1 and thus the mechanism involved is chemical adsorption. In the chemisorption process, the adsorbents adhere to the adsorbent through a weak chemical bond and thus this process is associated with relatively higher adsorption energies, Hardal and al. 2011. For conclusions. In this work, the removal of methyl orange from aqueous solution onto CHT/nZVI and nZVI has been investigated. The adsorption results showed that the CHT/nZVI is an effective adsorbent for removal MO with high adsorption uptake, 19.31 mg/g, under the optimum operating condition, 120 minutes contact time and adsorbent dose 1 g/L. The Freundlich isotherm showed a better .T than the Langmuir and Temkin isotherms, thus, indicating the applicability of heterogeneity of MO on CHT/nZVI and nZVI. The adsorption kinetics was found to follow closely the pseudo-second-order kinetic model. Results from this study suggest that CHT/nZVI and nZVI are a very effective adsorbent for MO. Conde of interest. The authors declare no conde of interests.